So I want to introduce Ahmari. Dr. Ahmari. He is assistant professor for the Department of Civil Engineering at the University of Texas at Arlington and a licensed professional engineer in Texas and Ontario, Canada. He has more than 20 years of industry research and teaching experience in the area of water, resources, environmental hydraulics, and river morphology. Before he joined UTA, he worked for 10 years in Canada, where he led several environmental impact assessment studies for hydroelectric dam projects. So today he's going to talk about stream crossing bridges that are designed to withstand hydrodynamic loading, which I'm super excited to hear about. So pleased to help you welcome him today.
Thank you, Julie. Good afternoon. Maybe it's still good morning. Thank you so much for being here. This is my first time presenting at ASC Dallas. I'm sorry. I hope the presentation would be helpful for you guys, whatever you're doing, consulting, construction companies, or other entities. So today I'm going to talk about assessing and enhancing stream crossing bridges subjected to flood events. As we know, the bridges, stream crossing bridges, are very important in terms of the transportation infrastructure. They connect cities, towns, rural areas, urban areas together. And then in the case of the flooding, if they fail, they may cause so many problems in terms of accessibility, no emergency procedures or evacuation procedures will be all interrupted. So what we do in terms of designing such a bridges as river crossing bridges, we design them for certain flow scenarios. Let's call it design flood. But we have seen that across the US and around the world, there are many bridges that are failing due to flooding. Even though there are other causes for the failure, bridge failures like a tsunami, earthquake, and other cases, but flooding is the major issue for bridge failure. The reason basically is attributed to more frequent flooding we have and high flood frequencies that we are seeing, and also the complex behavior of the bridges under the flood conditions. So what we have done in this project that is funded by TxDOT and basically performed at UT Arlington, we have looked at the bridge scenario with different geometry under different flow conditions. We ran hundreds of experimental tests in the lab and many CFD modeling, computational fluid dynamics modeling. And also we have done some structure analysis to see how these bridges behave under flow conditions, different flow conditions, and then how we can make them safe, either for the future bridges or current bridges. It's not moving.
Apparently it's, there we go. No, it should
Good.
work.
Okay, thanks so much. So today I'm going to talk about some of the background information about this project. I'm going to talk about the physical modeling that we have performed. I'm going to talk about the numerical modeling as well as structural analysis. And finally, the recommended mitigation measure that we have come up with for making bridges safer against flow hydrodynamics. As you can see in this picture, between 1989 to 2012, more than 800 bridges failed in US for different reasons. But if you look at the stat on this side, on the right side of the picture, so you can see the major cause of the collapse in bridges are attributed to either flooding or scouring, which is all hydrodynamic issue. So more than 60% of bridge failure that happened in US just happened because of the flooding. This is one example that we had back in 2015 in US during the Memorial Day flood event. There was about 12 inches of rain, just poured down very quickly. The river water level rose about 35 feet, and there are several bridges failed in Texas, Kimberly, the other one, Fisher Road. So you can see the bridges, how the collapse happened and how this situation caused some significant damages to the economy and accessibility to the region. If you focus on the Texas only, the TxDOT or Texas in general is the largest inventory of the bridges, more than 500,000 bridges. In US, we have about 10% of that is basically in Texas. In Texas, the way we design the bridges is 400 years slot, considering a little bit of 4 inches of freeboard. But we have seen many bridges that basically, even during the 20-year or 50-year flood, are inundated, either collapsed or partially damaged. The TxDOT design policy requires designing the bridges for 100 years flood, at the same time consider some mitigations for hydrodynamic forces, including the shear keys or ear walls. So example of shear keys you can see on the right side of the picture in the bottom slide. So basically, these are the measures that is in place, but as I mentioned, we have seen many bridges collapsing, even under flood condition, 25 years, 50 years or low. And the reason would have been so far, either we have significant velocity in the stream or we have significant debris that is brought by the flow. So our approach in this study was conducting a scale modeling in the lab of 4 different bridges in Texas. TX girders, we look at the box beam, we look at the slab beams, and then we did the computational dynamics, looking at the scenarios that we could not handle in the lab because of the limitation of the physical modeling. And eventually we have developed the final element, the structural models of the bridges, and look at the forces and compare the forces with the resistance or shear forces that we have in place based on the current practice. And if we found that those forces are larger than existing resistance, we came up with the recombination mitigation measure for those cases. In terms of physical modeling, we had 4 different tasks, starting with design a scale model, and then measuring flow and forces during different scenarios by several instruments. Then we have conducted the scale model on 4 different bridge models that I mentioned, and then eventually we have developed the force and moment coefficient design charts. This is our experimental setup. The flow was 17 feet long, 1 foot wide, and 1.5 foot tall. We have built our scale model of aluminum, which has the same, almost the same density as concrete, reinforced concrete. We scaled bridges 50 times smaller. We built girders, decks, as well as railings, and substructures that I'm going to show you later on. We have measured flow, velocity, discharge, depth, so on and so forth, and forces and over 30 moments with the instrument that we have attached to the bridge. Here, this is the bridge, this is the load cell, this is the torque cell. We connected them and we measured them during different flow scenarios. So these are the bridges that we have modeled. We look at 2 different bridges in terms of road base, 24 feet road base and 46, 46, 24 and 44 road base. And we look at 4 different beams or girders. The first one, bridge number 1, is I-28, TX28. The second one is TX54. Then we have a box beam. Here, the Boxfield 28 and Slab. So these are the scenarios in terms of superstructure that we look at it. We also put the more common type of railing here in the model. So this is just an example of how we scale down the bridge size. This is TX28. For example, the deck thickness is around 9 inches in reality. In practice, we scale it down to 0.19 inch. In the lab, or for example, the girder height, as I mentioned, is TX28, 28 inch tall. So we scale it down to almost half an inch. So these are the scale down dimensions versus the actual dimension. Same as the substructure, to look at the piers, in case that you have piers in this stream, and bend cap, bearing pads, bearing system, everything was simulated in the lab, in case that you want to look at either just superstructure, how hydrodynamic forces act, or the combination of having a superstructure, substructure in some wide channels that you have, both abutment as well as the piers. As I mentioned, the debris is one of the significant causes of the bridge collapse. Here we look at two different debris. As you can see on the right picture, at the top, sometimes you have debris, branches, trees are coming up to the bridge and basically pile up on top of each other, making a vertical wall. This is one scenario, we look at it and we simulated it using a flat plate debris here. There are some other cases, the debris is just basically accumulating in the flow direction across the channel and forming a wedge type of debris. So we simulated both of them using wood material here in the lab. Also, we look at the effect of the skewed of the deck on the hydrodynamic forces. So not all the bridges are straight. Bridges flow is not always perpendicular to the bridge. So how the skewness would affect the forces and how that would affect the stability of the bridge. So besides looking at the 0 degree skewness, we look at the 15, 30, and 45 degree skewed based on what we have been seeing in the field. The other thing that we have seen in coastal area is a surge. Surge and the wave are one of the major components to the flow that would cause the bridge collapse. So we look at the surge with different surge height, length, as well as different initial still water condition and flow depth. So we look at this scenario as well. So the test condition for the flooding, we collected more than 300 bridge data across Texas, either in the inland area or the coastal zone, to come up with the flow range that we need to look at. So the flow range would include the depth of the flow, the velocity, as well as how close the bridge deck is to the stream bed. But we incorporate all these numbers together to come up with some dimensionless numbers. That was explained here. The first one is inundation ratio. How much bridge is inundated? So there's a measure saying that if the flow is just below the girder, bridge is not inundated. If the flow is at the top of the railing, inundation ratio is 1. If it goes up and up, so the bridges get more flooded and flooded. So we look at the basically 0.25 inundation ratio to 3. So to incorporate the depth of the flow. The proximity ratio explains how close the bridge is to the bottom of the stream. If the bridge is too close to the bottom of the stream, there's a lot of increase of the velocity, a lot of scouring might happen, and then that will change the flow regime entirely. So we look at the cases that the proximity ratio was around 1 to 5. So very deep channel or very shallow channel. Also look at the velocity, but in terms of fluid number, how much fluid number was. In the field, we have seen fluid number from 0.1 up to 1 with the average of 0.35. We could not go beyond 0.34 in the lab, so that's the maximum fluid number we tested. But during the CFD modeling, computational dynamics modeling, we tried higher fluid number up to 0.9, making sure that we cover the entire range of observed flow. And then we have a blockage ratio in case that you have a substructure and you have debris. How much of the flow, the entire flow, is blocked by debris or by the substructure that would cause changes in hydrodynamic forces. So this is basically, the test condition for surge, as I mentioned, one of the components. So we look at different water depth. So model is 8.5 inches, but in reality is 425, which is about 30 feet. Depth of the flow up to 40 feet in the prototype. We look at the wave period, we look at the wave height, and also the clearance height, as I mentioned, different water depth before the surge starts. So the scenario we look at here, basically, hybrid I-28, two different roadways, 24, 45, different skewness we tested, and then 45, only with the 0 degree skewness, but two different roadways, slapping, boxing, so on and so forth. So we try to have as many scenarios as possible to look at different geometries and different fluid conditions to come up basically the design charts for all these type of bridge geometries. So here basically you can see the shot of the bridge under the experiment. Here you see the TX28 on the left, and then you have TX54 on the right, and at the bottom basically shows all three forces in X, Y, and Z direction and the overturning moment that was captured during these type of measurements. So these are the test series A to F with a different combination of the bridge geometry, different flow conditions, skewness. If you have bridge with the substructure, superstructure here, we put the deck on top of the substructure without any contact. We wanted to measure the forces. And then we put the deck on top of the substructure. We remove the gauges to see if the bridge will collapse or not by the hydrodynamic forces. And eventually we look at the basically bridges under the wave action. So these are different scenarios that we look at, a combination of flow conditions, geometry, as well as flow versus wave. So this is an example of test A. You can see on the left side, you have 24 feet roadway, on the right side, 44 feet roadway under different geometry, TX28, TX56, box beam, and a slab beam. I'm just quickly go over this slide. Here we have straight, basically deck versus a skewed deck from the top, 30 degree, 15 degree, 30 degree, and 45 degree skewed deck. Here you see the debris modeling. On the top you have a flat plate debris. On the bottom you see the wedge debris we simulated, and we measure the forces in all directions, overturning moments. This is the scenario. We look at the substructures and superstructure together, but we have connected the system to gauges so we can measure the forces. So there was no connection between the substructure and superstructure, making sure that the bridge can move without having any friction. This is the one, basically we simulated the pad. We put the pad between the substructure and superstructure to see if the bridge will collapse under different flow scenarios or not. Here we look at the wave. As you can see, a different type of wave in terms of height, flow depth, duration, wave length, we simulated here. So once we have all the measurements in terms of the forces, we look at the forces that basically are primary forces applied on a bridge. This is just the superstructure. So forces includes, obviously, we have hydrostatic force on both sides of the bridge. We have buoyancy, obviously, pushing the bridge up. And then we have the drag force. These two are the dynamic forces. The first are the static forces, the drag force, pushing the bridge in the flow direction. And we have lift force, either pushing it up or putting it down, depends on the flow condition. And we have overturning moments. So we have the forces and moments measured by the instruments, but the question here is that what are these numbers, the coefficients we have, CD, CL, CM. This is basically how the shape of the bridge will impact the amount of the force. And this is not something we can just come up with. You have to have the exact shape and test it, and depends on the shape of the bluff body. In fact, these values may change. And there are some other factors, how the CD, CL, and CM will change. I'm going to discuss how we basically come up with these values. So this is one example for TX28. We have plotted the values for the drag coefficients for different scenarios in terms of inundation ratio. This is an indication of how much flow is basically how much bridge is inundated from 0.25 to 25. As you can see, the drag coefficient has a dip when the flow is inundated to the top of the girder, but it has higher coefficient for the hydraulic forces, for a smaller inundation ratio, or higher inundation ratio. Same thing, we look at the lift coefficient. So these are the negative values, mostly, meaning that for this case, the bridge is pulled down by the flow, and the maximum CD happens when again you have inundation ratio of 1, but when you get to the smaller inundation, higher inundation, this value goes to almost 0, meaning that the lift force is not significant. Same thing, you can see the moment coefficient has a small variation with the inundation ratio, but there is again inundation ratio of 1. So we ran many scenarios. I don't want to show all of them here, but this is just a summary of all bridges without the bridge, without substructure. This is just superstructures, but different geometry. So this is the trend we have seen for many cases for different geometry under different flow conditions. So you can see there is basically the higher bound, the lower bound of the lift or drag coefficient or moment coefficient that can be used for the design of a bridge. Depends on what type of flow condition we are dealing with or what type of bridge type we are dealing with. So based on the figures and relationship we prepared, these are the design equations for CD, CL, and CM. Either we can use a general equation for any type of bridges under any flow conditions, or we can just use equations that are developed based on a specific bridge geometry. So we have developed this equation, and then we look at the effect of the basically skewness here. So from 15, 30, 45 skew, this as well as the zero skew. You can see the zero skew is basically here, the color dot, the blue and green. And if you change the skew, obviously the lift, drag, and moment coefficient will change. But this information can be used when you're designing a skewed deck. This is also looking at the bridging debris, how blockage ratio would impact the change in the drag coefficient, lift coefficient, moment coefficient. So we have flat plane. The top obviously would create higher value of the CDCM, and then you have wedge debris is streamlining the flow, is not causing that much drag compared to the slab debris. So we have developed these charts also in case you are designing a bridge with debris. This is looking at basically the effect of the superstructure and substructure together. So these are the upper and lower boundary when we did not have any piers, but when you add the piers, obviously the blockage increases and would change the forces acting on the bridge itself. So if you're designing a bridge, it has abutments and piers, definitely the drag force would be much different from just a bridge across the road without any middle piers. So for the case, we tried to see if the bridge would collapse under this flow condition. The lab, it did not happen. We could not go as high as possible in terms of the flow depth, velocity, and the forces introduced to the bridge. So we didn't see any fail. But again, the limitation was the fluid number. First of all, we could not go beyond 0.34 in the lab. So we decided to look at the higher fluid numbers to the computational dynamic forces. So this is the effect of the basically wave. So obviously wave is not just like a flood. Sometimes flood could be steady, could be unsteady, but wave is periodic. So this is the forces acting on the bridge. So we have horizontal force and we have vertical force, and obviously vertical force is more effective on unstable in the bridge. And then we compare the forces. So these are the maximum and minimum forces. We have seen the dash line, the black dash line is the maximum minimum forces we have seen just for the flooding. But the green, the red ones are forces due to surges or waves. So in some cases, we have more significant forces because of the surges compared to flood forces. So another thing we look at basically the impact of bridge geometry on the flow condition. So we use the technology called PIV. I'm trying to see if I can run this one.
Do you want to run the top one or the bottom? Do you want to run the top or the bottom?
Both.
Both?
Yeah. Okay.
And then you'll just click right there and it'll run the bottom.
So this one basically shows you have a magic hand, I don't. So it basically shows how flow condition would be different under different bridge geometry. So this is the box beam. The other one was basically slab beam, girder, eye girder. And then we look at this corner.
Yeah. Do you run them both at the same time?
Yeah.
Okay. There you go.
So we can see how flow condition under the bridge would be different. Eye girder versus the box beam. The girders is sticking out, causing more break in the flow and disturbing the flow, and that disturbance will cause different, basically, force acting on bridge as well as coefficients for these forces. So in terms of the computational dynamics, basically we use ANSYS to look at the bridge scenarios that we could not simulate in the lab. So we simulate the exact type of flow we had in the lab, 12 feet. This is only 12 feet, but same width, same depth. And then we provide the mesh, obviously a smaller mesh around the bridge and larger mesh outside of the zone of influence of the bridge. And then to use the CFD modeling, we had to calibrate the model and verify the model with the experimental work. So the first step, what we did, we look at the validation model. in literature, there's a study by FHWA and some other research teams looking at this three-girder bridge. So we simulated this bridge to make sure that our model is working properly. And the result, as you can see, for the drag, lift, and moment coefficients are in line with what has been done previously by other researchers. Also, we validated our model with our experimental results. The validation worked to some degree, especially for the lift force. It was comparable. For the drag force was comparable with the inundation ratio of 1.5, but after that, the result from the CFD modeling was smaller compared to what we see in the lab. Obviously, the lab, you see whatever is happening, we trust. I'm an experimentalist myself, I trust more to the lab experiments. And this discrepancy has been seen in other places. There are always differences, but based on this practice, we basically look at the different scenarios after we found that we can trust the model to some degree. But here we extended the foot number values up to 0.9, making sure that we cover everything in the field. Also, we extended the inundation ratio up to 4 in some cases. We could not go beyond 2.5 in the lab. So we covered everything and we ran the model for all the scenarios we had in the lab. So these are some of the results. Similar type of charts we developed in the lab. We developed based on the numerical work. So these are some snapshots of the flow regime around bridges with the debris, flat plate debris, and basically wedge debris, how they impact the flow condition and flow regime. Once we completed this small scale modeling, CFD modeling, computational fluid dynamics, we simulated full scale of the bridges because now we need the forces. We need forces to compare these forces with the resistance forces by the bridges. So we basically repeat our experiments, but now the full scale with the ANSYS CFD modeling. And based on the full scale modeling, we found the forces acting on different bridge scenarios in terms of geometry, skewness, wave, debris, and so on and so forth. So you can see here on this column, the drag force acting on these bridges. In the last column, the lift, the buoyancy on bridges. Now we have the forces. The next step would be doing the structural analysis. So the same bridge model was used to do the structural analysis, look at the property of the material, and come up with the resistance forces by the concrete itself, by the rebars, to see if the shear key, for example, in this case, for ear walls would be enough to resist the flood force or not. So TxDOT uses shear keys, basically just a block of the concrete between the girders, hold down by rebars to make sure that if there is a force, lateral force, the deck is not moving. For box beam and a slab beam, they use the ear walls. So it's just basically at the end of the bed cap, they put ear walls, same thing. It's a block of concrete, hold down by the rebars, making sure the lateral force is not causing bridge collapse. So based on the girders, beams, piers, and all the elements, properties, we calculated the resistant forces, and even the friction between the bridge and the substructure. So these are the models we look at. We look at the eye girders again, the box beam, the slab beam. You can see the shear key. It's the standard practice by TxDOT, having one shear key, and they have the ear walls for these slab beam and box beams. And then we look at also the effect of the debris as well as the waves, as we did in other experiments. So I don't want to go through all these details, but this is basically how the capacity of the shear key is calculated based on the friction between the materials, as well as the resistance that is provided by rebars. So this is the details, basically the TxDOT details for the shear key, the thickness of the shear key, you can see the number of bars you have and the size of the bars. This is the ear wall, the typical ear wall, TxDOT details. So these are the forces I mentioned. We have the drag force pushing the deck. You have the friction between the substructure, superstructure resisting the movement, and then you have the shear key also resisting the movement. You have the uplift force, you have the drag, you have the buoyancy, and you have basically the hydrostatic forces. So all these forces are combined, but to be on the conservative side, we decided not to account for the frictional resistance. We just relied on the shear key and ear valves to hold the bridge in place during the flood. So here basically is the detail of how we calculated how much enforcement we have and how much basically resistance we have for different regions. Then we want to compare the resistance versus the applied forces. That was the idea. So this is basically the summary of the resistance forces by shear key. For example, here the first line, if you have 24 roadway TX28, what would be the total force that can be resisted by the shear key? 716. Now, we have 716, but the force we got from the modeling is 799 for case 1. Meaning that under the flow condition, if the fluid number is 0.9, severe flood condition, the bridge cannot hold down. They just collapse in that condition. So we need to do something for that case. With the other cases, bridge seems that they are working very well with the current practice of TxDOT. Here, TX54, the red one is the areas basically. The drag force is larger than the shear key or ear bar capacity. So it means that we have to do something about these cases. Same thing here, when you have a debris or wave, there are many cases that we have to do some mitigation to make sure that the bridge is not moving. Same as box beam and slab beam. There is a need for some mitigation when the fluid number is 0.9, very severe flood condition. So the solutions or recommendations, basically, these are the recommendations we just gave TxDOT a few days ago. Instead of using one shear key, we can use 2 shear keys. This is one of them. This is for TX28. The other one is just basically increasing the reinforcement from 2 legs per line to 4 legs per line. So basically it's shown here. So this is the current practice. You have the rebar, 2 legs, and then to increase to 4 legs, obviously increase the resistance. So that's a solution, recommended solution. For TX54, even 2 shear keys may not work. So we recommended adding 3 shear keys. So basically using the existing design, but adding more shear keys, which is a simple solution. Or the other one is also increasing the 2 legs per line to 4 legs per line. For a slab beam, the situation is a little different because the slab beams, you have ear valves on the 2 ends. You don't have much room to add more ear valves. So the idea is to extend the bend cap and increase the size of the ear valve. Basically, additional 24 inches. So this is the existing detail. This is the recommended one. So the gray area extended the ear valves by 24 inches. Option 2 would be going with the 18 inches additional length, but changing the amount of rebar. So box beam, same thing, extending by 18 inches to make sure that you have enough resistance. And the conclusion, basically, we look at the 150 scale models in the lab. We look at different bridge geometry, different flow scenarios, and then we came up with the design charts for different conditions. And then we tested all these things in CFD modeling to make sure that we cover the entire range of the flow that has been observed in the field, especially the fluid number, which is significant, has a significant effect on the force. Then once we have this bridge model built as a full scale, we measure the forces, calculate the forces and compare it with the resistance forces. In some scenarios, we saw that the applied force is more than the demand. And then for those cases, we recommended some modification, and that's up to you to TxDOT, I guess, to adopt them or not. So we're just going to be talking with them in the next few months. Thanks so much.